Okay. And now while Km is a constant, Vmax is not. Vmax depends upon the number of enzyme molecules. So we can normalize to the total enzyme concentration. We know how much enzyme we have in the reaction, or we should. So if we take Vmax, which is going to be molar per second, divided by total enzyme, which should be in molar, we get a rate constant, kcat, the catalytic rate constant. And that's going to be in units of per second. So how many reactions per second? So this basically tells you the maximal rate of an individual enzyme. That's how many reactions can it catalyze per second. So if the kcat were 1,000 per second, that means each enzyme could catalyze 1,000 reactions per second when it was working at its maximal rate. Here are rate constants for a few different enzymes. Catalase is one of the world record winners, so 40 million reactions per second for breaking down hydrogen peroxide into oxygen and water. Of course, it will never be that fast because you would have to completely saturate the enzyme with substrate. And Rec A is down at 0.4. So you have a large range in kcats. We can define a specificity constant kcat over Km, and that is how good the enzyme works with that specific substrate. So if you think about it, the higher the kcat is, the better the enzyme is. The lower the Km is, that is, the less enzyme it needs to be saturated, the better the enzyme it is. So if you have a high kcat and a low Km, this number is going to be very high. Okay? And if you have a specificity constant around 10 to the 8th to 10 to the 9th per molar per second, that means it basically can't go any faster. That's catalytic perfection. Essentially, the rate's limited by diffusion of substrate to the active site, because once it gets there, it gets turned into product instantly. Okay? And here are some of these enzymes. So we were looking at catalase a minute ago, 4 times 10 to the 7th per kcat, but its Km is about 1 molar, so not a very good Km. But so kcat over Km is about 4 times 10 to the 7th, close, approaching 10 to the 8th. Acetylcholinesterase is better. Its kcat's lower, but its Km is around 90 micromolar. Okay, so much lower Km. So its kcat over Km is around 1 times 10 to the 8th, 1 to 2 times 10 to the 8th. So that's about as good as it gets, although crotonase here is even better, about 3 times 10 to the 8th per molar per second. So when an enzyme gets that good, it essentially can't get any better. So, all right. Now, when you have substrate that's much lower than Km, which is the regime that some enzymes work in, then essentially, if Km is much greater than substrate, then this term down here kind of simplifies to just Km, right? And so the rate is basically Vmax times substrate divided by Km. And since Vmax is kcat times enzyme total, we can substitute that in, and we get this relationship here. The velocity is about, that is when substrate is lower than Km, the velocity is about equal to kcat over Km, the specificity constant, times the total enzyme concentration, times the substrate. Okay, and this kind of makes sense, because basically what this is telling you is the rate of the reaction is about proportional to the amount of substrate. That is, if you double the substrate, you double the rate. The amount of enzyme, if you double the enzyme, you double the rate. And the specificity constant, that is how good the enzyme is. If you double that, you double the rate as well. Okay? So that is this regime here, where the substrate is below Km. It's essentially about Vmax over Km times S. That is this guy here. When it's getting to completely saturated, then it's approaching Vmax. So basically, this hyperbolic curve is in between this linear rate and this line here, where it's Vmax. Now you might ask, what do these numbers actually mean? Okay, a lot of enzymes don't actually operate under the simplistic mechanism that we started with. You might have enzyme binding substrate in one conformation, changing to another one, changing to another one, changing to product, releasing product. Now I've got 1, 2, 3, 4, 5 times 2, 10 different intrinsic rate constants in principle. That's not how we started with. And yet, they still follow this behavior. Even so. Okay, so what do these mean? Usually we don't know. If one of the steps is really slow, much slower than the other ones, and that's the rate limiting step, and kcat will be more or less that rate. Okay, but if they're comparable, then the kcat is going to be a complicated function of all the rate constants. And so teasing those apart is very difficult. Also, I want to remind you, Km is not the dissociation constant in the enzyme-substrate complex, although many people use it that way. It really isn't. In a very simple case, where the dissociation rate is much higher than the catalytic rate, then it approaches that, okay? So let me just give you an idea. Like if you remember how we started, okay, if we have enzyme plus substrate forming enzyme substrate complex, and that releases product, that really simple. And so the equilibrium constant is actually, so the dissociation constant is really K minus 1 over K1, right? This rate over that rate. That would be the equilibrium constant for this. Km is K minus 1 plus K2, catalytic rate, over K1. But if this rate is kind of slow, and this rate, these two rates are really high, that is, essentially the enzyme is in equilibrium with its substrate. If K minus 1 is much greater than K2, then Km, that is, this term here is pretty much K minus 1. Okay? So it simplifies to K minus 1 over K1, which is the Kd. So in that case, then the Km would be pretty much like the Kd if this catalytic rate were slow compared to association-dissociation of the enzyme-substrate complex. But that's not the case for a lot of enzymes. Okay, and here's some Kms you might find. Actually, you can have some Kms that are in the micromolar range and so on, just to give you an idea of different Kms that exist for different enzymes. Okay, that's where we're going to stop.
Aló,
No gané nada, bebé.
aló,
Aló.
¿en
No gané nada, bebé.
qué no van a hacer nada?
En mi grupo de hackers.